The Darlington transistor is sometimes also called a Darlington pair. When looking at the single component, this is the basic construction. We'll get into that in a moment. But we can also get the same type of effect if we look at the actual transistor using discrete components. We've got a collector, an emitter and a base, and we can see just from this already that seeing as these are silicone components, we can already see that we will have a 0.6 volts across this base emitter along with a 0.6 along this base emitter, and as a result for this pair to conduct we're going to need 1.2 volts instead of the 0.6 volts for a normal transistor. The basic construction, when looking at the actual component, we can obtain this just by the way from using single NPN transistors. When looking at the overall component, we see that we've got a collector that connects to a large N-type material. We've got a base that connects to a large P-type material. We've also got the small N-type material over here that links through an internal conductor to the P-type material over there to bypass, in essence, the PN junction formed between that N and P-type material. And then we've got the emitter N-type material that is placed in that corner over there. The circuit symbol for the Darlington pair or the Darlington transistor looks as follows. We've got our first transistor that feeds into a second transistor, and then that circle there refers to this as a single component with a base, the collector and the emitter as we would have a normal NPN transistor. Now the way that the operation works, the emitter connects to a negative, the collector connects to a positive, and when we connect a positive voltage onto the base that is greater than 1.2 volts, then the transistor will become conductive. Electrons flows in from the emitter into the P-type material. That causes an influx in a negative charge on the base material. That negative charge forward biases the PN junction between the base and the collector, and then we will have conduction taking place towards the collector. The characteristic curve looks very similar to a normal NPN transistor. The difference, however, is this. We get that delayed switching. This delay over here, or this leg, is caused by the biasing required by the base emitter junction at 1.2 volts. This still refers to my base current, typically measured in microamperes. Horizontal refers to the voltage across the collector emitter junction, and then my collector current, typically measured in milliamperes, is indicated on the vertical. As repeatedly stated, we require a 1.2 volt connection between the base emitter in order for conduction to take place. The advantage with the Darlington transistor or the Darlington pair is that the overall gain of the pair is calculated not as the sum of the individual transistors but as the product of the individual transistors. So as a result, equal to the gain of transistor 1 multiplied by the gain of transistor 2. As all transistors, it has two applications. First application is as a switch. The switching circuit will have our positive supply voltage connecting through a resistor or a load, and that will feed into my Darlington pair. That connects to my 0 volt supply, and then the input over there, to ensure no stray voltage is activated, we connect 0 volts through that base resistor, and then we've got a switch which connects to a voltage that is greater than 1,2 volts in order to switch the transistor on. Second application is as an amplifier. That is done by means of our typical biasing circuit for our Darlington transistor. Our base biasing resistors on the input, our emitter resistor, we can add a emitter capacitor. That there is my Darlington pair, and that feeds to my output voltage with my input voltage over there. Must always remember the positive and the negative supply voltages when working with amplifiers.